In the last video, we discussed the definition of the electric field and how we could use that definition to calculate the force on a charged particle. Now the question is, how do we find the electric field? One of the most important objects or ways that we can work is to work from point charges. So this is something you should know off your head. The electric field due to a point charge. So it's a special case, but as I'm going to explain later, it's a very important special case that using modern techniques such as spreadsheets or computers we can use to work even problems that don't directly work off the formula by itself. So I want you to memorize this formula and to know it because we're going to take and use a lot of it. The electric field due to a point charge is equal to K times the value of the charge Q divided by the distance from that charge squared R hat. Now what does this tell you, or what does it mean? What I'm saying is this: if we take a charge Q and we think of that charge as being at an origin, remember we can move our origin anywhere we want, and we go some distance out to some point in space, a distance r, then the electric field at this point is going to, if the charge is positive, point in that direction along this radius vector, and its magnitude is going to be K times the magnitude of the charge Q divided by this distance. So as you get further away, the field goes down, and it goes down as r squared. Why? It goes down, remember this K has a 4 pi, so it's 4 pi r squared, the surface area of a sphere. The lines we're going to show you spread out, and it's the density of the lines that gives the strength of the field. And they go down as the area, and the area is 4 pi r squared. This equation does not work for most things. It only, in fact, works for a point charge or a spherical charge when you're outside the sphere. For instance, over here at point X. Now, I remind you what K is. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared, right? And we also know that you could rewrite K as 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Let me prove to you that this formula is true, and then we'll show you how we're going to apply this formula. Consider that you had two test charges. This one Q that we're going to consider to be the cause of my electric field, and a test charge little q. So in this case, we're talking about here being our origin, and this is my test charge. And if you put a test charge there, we find the force on the test charge and divide by this charge. By definition, that's the electric field. Well, I know how to calculate the force between 2 point charges. That's called Coulomb's law. So the force is K, charge of the first, charge of the second, over R squared, R hat. That's just Coulomb's law. So now that I've got the formula for the force, I just need to divide by the charge. So by definition, E is F over my test charge, which was Q. So I have K, Q, little q, over R squared, R hat, and then I'm dividing by little q. That little q cancels this little q. And so I have the electric field is K, the big charge that's creating the field, divided by R squared, R hat. Quod erat demonstratum, that which was to be proved. Alright? Now, unless Coulomb's law was working, then this formula, which is derived from it, isn't true. And Coulomb's law is only true for point charges and spherical charges. All right, so it won't work for a rod. It won't work for a plate. So you have to be careful. We'll need to find other techniques for them. But a lot of problems involve point charges. For instance, we can consider the nucleus to be a point charge. We can consider an electron to be a point charge. We can use this to do atoms in chemistry. So there's lots of things we can use this formula for. So you need to memorize it. All right, let's use this in a problem. Example, what is the electric field at point P, which is located at a distance 2 meters from a 4 Coulomb point charge? Now, 4 Coulomb point charge is a ridiculously high charge. More likely it's some sort of a nanocoulomb charge, but we're talking about point P right here. And we want to know the field. Now, the first thing to do is to find the magnitude using our little formula. I've got my XY axis all set up. The magnitude, E, would be K, and the magnitude of Q, because we're not going to count any of that R hat or signs, that's directions, divided by R squared. So that'd be 9 times 10 to the 9 Newton meters squared per Coulomb squared. We'd multiply by the charge, which says it's 4 coulombs. And we divide by the distance, 2 meters, which we square. Well, we can see that this 2 squared is going to cancel that 4. So the number works out really nice for us. E is going to be 9 times 10 to the 9th. The meter squared cancels that meter squared. And one of those coulombs cancels one of those coulombs, and I'm left in newtons per coulomb. Now we need to find the direction from the diagram. So, remind you, there's the charge, Q, and we're looking out at this point here, and that Q is a positive charge. So if I was to put a positive charge here, if I was to think of there being a little positive charge, Q, that charge would see that positive charge and be repelled. So that means that the force is in that direction. But the direction of the force is the same as the direction of the electric field. So E points in X direction. Now that we know the direction, we can combine everything up that we want for finding the field. Let me finish this. E is equal to 9 times 10 to the minus 9 newtons per coulomb I have. Find the magnitude, then ask which way it pushes. If you're lucky, it lies along the X or it lies along the Y, but it might not. It might, in fact, be that you're asked to find the electric field, say, up to some point here. Then, the electric field in this case would point like this. And we would need to know that angle, just as we would have that same angle here. And we would need to break that into X and Y components using trig. So we'd find the length, the hypotenuse, we get the angle, we'd use trigs to find the X part of the electric field and the Y part of the electric field. Now let's say that they changed the problem and they now ask me what's the force that a minus 3 nanocoulomb charge would experience at point P. Well, this is very easy because it's just QE, and since I've solved E, all I got to do is take minus 3 times 10 to the minus 9 coulombs and multiply by my electric field, 9 times 10 to the 9th newtons per coulomb I hat. Notice that the coulombs cancel. Notice the 10 to the 9 and 10 to the minus 9 cancel. And the force is minus 27 newtons I hat. Once you have the electric field, it's really easy to calculate forces. Now, you change the charge on me. You change the charge, I don't have to recalculate the electric field. All the difficulties was in E, just as all the difficulties in calculating weights are in the G. All I got to do is multiply by nu Q. So if you put a different charge there, say a 5 Newton Coulomb charge, F is 5 times 10 to the minus 9 coulombs times 9 times 10 to the 9th newtons per coulomb I have. And again, kills this, kills that charge, and the force in this case is 45 newtons, but it's in the positive x direction. And you can keep putting new charges at point P all you want, and I can just keep turning out forces right and left. If you've got the electric field, it is easy to calculate force. The difficulty is calculating the electric field, and what we're doing is giving you a way of handling the electric field, and that is through this formula. But it only works for point charges. In the next video, we'll talk about what to do if there's more than one point charge in a problem. I'll see you on the next video.